Hello, lovely further people. What I'm going to talk about in this video are topics that are on the test. I am going to take the first question from each of the sections on the revision sheet that I've sent you and go through them in detail and also kind of just talk generally about each topic. Hopefully it might help. So firstly, on the assessment, we have got dimensions. So dimensions is definitely a year 12 topic. Dimensions is year 12, but I think that was maybe the very first thing that you did in year 12. So you may just need a little bit of a reminder on that. And then centres of mass. So centres of mass, that was a year 13 topic. And things that we've looked at are finding the centres of mass of flat shapes. So they were called laminar, but also three-dimensional shapes. So cones, spheres, and so forth. But then we looked at non-uniform flat shapes. So we looked at integrating, and then we were also hanging them from points and finding the angle at which they were hanging. So that's a centre mass. And we've also fairly recently, but it was kind of straddling Christmas, wasn't it? Looked at impulse and momentum. So we were looking there at collisions in 2 dimensions. So oblique collisions. And also impulse in 2 dimensions. So that was the impulse momentum triangle. Impulse in 2 dimensions. Circular motion. So circular motion, it was kind of mostly year 12, wasn't it? It was mostly a year 12 topic. The year 13 bit was a bit of an add-on, wasn't it? Looking at the projectiles afterwards, there was a bit on transversal acceleration, but it was mostly year 12, vertical and horizontal motion there. And the last topic we've just done, so actually I'm not going to talk about it in this video because hopefully it should be fairly fresh in your mind. So it's called variable force, but we're looking at motion with variable acceleration, variable velocity, variable displacement, variable force, variable power. It was variable anything, wasn't it? So essentially it's using differential equations in the context of mechanics questions and applications. Okay, so they're the topics. Hopefully they're not too unfamiliar. That was always going to happen, wasn't it? I'll leave it there. So the first one, dimensions. So this topic here, I think it's just a matter of reminding yourself about it. I don't think that you're going to find this tricky at all. There's a slightly odd bit of notation there. So we would refer to, so it's mentioning here specifically force. And we would say that the units of the force, it's got this kind of square bracket notation that looks like that. And then what we say as well is that we say, okay, right, force, we know force is in newtons, but we talk about the SI units. So we split everything into mass, length, time. Is there another one that I've forgotten? Mass, length and time. So force, because the force is mass times acceleration. We would write the mass, we use capitals here as an M, acceleration meters per second squared. So meters, we use an L for length, per second squared. So of course that's t to the power of -2. So it's slightly confusing in that we use mass, obviously kilograms, which is M. We have got our length, which is measured in meters, but we call it L for length, and then time, it's measured in seconds. So we call it T. So that is what we use, and we express all of our units in terms of our M, our L, and our T. So let's actually look at the question. So the question says, by using dimensional analysis, find the dimensions of G. So what we've got what we've got here is an equation. F is equal to big G, M1, M2 over X squared. And we know that because F is a force, I've already worked out what the units of force are. So I've got it up there in green, MLT to the -2. I've also got an M1 there. I believe M1 was a mass. Yep, a mass of a planet. So M1 has got dimension M. M2 has also got dimension M because that is a mass, and the dimension of X, well, it's the length. So the dimension of X is L. Of course, I'm going to be dealing with an X squared there. So then we can just, it's effectively substituting in, isn't it? So if I consider what's going on with the dimensions, so looking at the dimensions, I'm going to rewrite my F equation. Oh dear, sorry, dimensions. I get the F, which has a dimension MLT to the -2, is equal to G. And to be consistent, we must make sure we write that down in terms of dimension as well. I've got M is the unit of M1, M is the unit of M2, and then L squared is the unit of X squared. Sorry, unit dimension, I should really be saying. And now we just want to rearrange the equation. We want to rearrange the equation because we want to know what the unit, sorry, the dimension of G is. So you can cancel M from both sides. So that's going to take me to multiply through by the L squared. So it's going to make me L cubed. I have a T to the -2 already there, and I'm going to be dividing by the M. Oh, I should be consistent, shouldn't I? Let's just stick with negative powers. So the units of G, dimensions of G, I'm not sure how naughty that is to refer to it as unit rather than a dimension, but I think strictly it should be dimension. So there we go. So using our dimensions, substituting what you know, remembering to use combinations of M, L, and T, and it's just a simple rearranging at the end. And this is an OCR question, and yet, you know, 3 marks. I don't think that's too tricky. Okay, now the second part, the lifetime of a planet. So the lifetime T. So we of course know that lifetime, it's a time that's going to be measured in terms of T. I've got a mass here, so K is a constant, so we don't need to worry about that when I do my dimensions. The radius, so I know that R is a length. G, of course, is what we've worked out in the previous part. Now, of course, there is a distinction, isn't there? And they are very good here. They talk about a dimensionless constant, and then we've got our constant G. So you can have constants, of course, you can have constants that have got a dimension. So many constants we just think of as a number, but of course have got a unit attached. So for example, g, meaning little g, 9.8, that's a constant acceleration. And of course we know it's got a unit of meters per second squared. So I'm going to use this equation here, but I'm going to pop the dimensions in there. So I'm just going to rewrite that equation out again. So I know that t is equal to k m to the power of alpha, r to the power of beta, g to the power of gamma. So considering the dimensions then, I know that t, which is time, is equal to, so I'm not going to worry about the k, but I know that the dimension of m is m. It's a mass, so it's going to be m to the power of alpha. The dimension of r is the radius, so the dimension is l, so it's going to be l to the power of beta. And the dimension of g, of course, is that kind of great big unwieldy thing there. So l cubed, m to the minus 1, t to the minus 2. And that is all to the power of gamma. And of course, what we do now, it's a technique that we've used in lots of contexts. We compare coefficients. So let's firstly compare coefficients of, I don't know, t. T comes up first. We can work out t directly, can't we? Because it wouldn't make sense to start with m or l because they're also combined in this bracket. So they'd have two powers attached. So comparing coefficients or powers of t. So it's not coefficients, is it? It's powers. I've got a t to the power of 1 there. So 1 equals, and all I've got here is this minus 2 with the gamma. So gamma is equal to negative 1/2. If I then compare powers of m, let's do m next. I've got 0 m's on the left hand side. On the right hand side, I've got this term here, which has got a power of alpha, and then I've got 1 appearing in there, haven't I? So that will be plus -1 times by alpha, and I know that alpha is -2, so gamma. So negative gamma is -1/2 plus 1/2. Sorry, I think I've made a bit of a meal of that. All I'm doing is I'm putting that into there, isn't it? I just made a bit of a wordy statement about something that's, of course, very straightforward. And last up, if we can compare powers of L. On the left-hand side, I've got none. On the right-hand side, I've got L to the power of beta, and then I've got L cubed to the power of gamma. So that will be beta plus 3 gamma. And gamma is -1/2, so that makes beta equal to -3/2. So the questions based on this always look a bit scary because, of course, they're always on formulae that you don't know. They're always talking about bits of, generally it's bits of physics that we don't know. It doesn't matter at all whether you've heard of the equation, whether you know what big G is, and I'm sure some of you will know about big G, but it genuinely honestly doesn't matter. It's just a matter of putting those dimensions in, and it's all about playing around with powers. That's everything. Sometimes it asks you to do subsequent parts of the question where you might be asked to play around with the formula you've just discovered. I don't know, bung a few values in. But again, even though it looks unfamiliar, it's just a formula. It's a formula that you can work with using our maths rules. So sometimes it looks scary, but look, 5 marks on that last part. That was 5 very easy marks. Look, 5 marks just there. How often does that happen in a further maths question? 5 lines and 4 marks. Okay, right. Okay, sense of mass. A couple of different things going on here. Firstly, you've got uniform shapes. So if you've got uniform shapes, and by uniform shapes, I'm meaning shapes that we can easily spot where the centre of masses are. So, okay, I might have a square there, I might have a bigger square there, I might have a, you know, something going on there. We could even put on a quarter of a circle there. We know where by symmetry or by general results, we know where all of the centres of mass are of the individual constituent parts. And then what we say is each one of those has a mass. So M1, M2, M3, M4. And quite often that mass we can think of as an area. So if they're made out of the same substance, area ratio is the same as the mass ratio. But I know that if I take all of those individual masses and multiply by the distance to the x-axis, so in other words, if I work out M1 x1 plus M2 x2 plus M3 x3 and M4 x4, then that will be equivalent to the mass of the whole thing, which of course is the sum of all those individual masses multiplied by the overall x bar. And we generalize that. We also, wrote that in vector form because there is a similar result for y. So also I know that m times by y bar is equal to sigma, all of the m's multiplied by all of the y's. Put a little subscript on if we want. We're going to do one of those shortly. We actually, I think in the end, preferred writing it in a table form, although I know some of you just would write down the calculation without necessarily all the working out there. There are all of the geometrical results, so they're just all listed on the formula booklet, so I'm not going to go through those. When it comes to finding the centres of masses of non-uniform shapes, so I'll just draw something that looks like something we might integrate. So you can either learn this formula or kind of learn how to just quickly get to it yourself. We want an equivalent of what's going on here on the right hand side. So think about the area of that thin strip. The area of one of those strips is a height of y multiplied by a width of delta x. So if I do a similar thing to multiplying that area, which of course I'm taking area to represent the mass because this will be made out of a uniform material. I want to multiply that area by that length, and that length of course is x for each individual strip. So the equivalent to the M1 x1, which we call the moment, but the centre of mass part for that particular bit will be x, y, delta x. We need to add all those up. So adding all those up as we did up here, but of course what we are doing is we are taking the integral because we need to take the limits. And then the left hand side, the bit equivalent to this here, well, the that is equivalent to the mass, which is equivalent to the area because we are going proportionally, and the mass or the area is just simply the integral of y dx. Sorry about my strangely differing colour pens. So we have got to work out the coordinate of the x. You've got x bar, oh dear, is equal to, instead of y rather, we can write x. So x f of x dx over the integral of f of x dx. And it looks very similar to a mean, doesn't it? Think about means from frequency tables. X times by a frequency. So we would write in a bracket GCSE sigma fx over sigma f. It's exactly the same form. We're essentially doing the same thing. A centre of mass is the mean of all of the individual masses. It's a little bit more awkward. This time we want to be considering that point there, but its distance to the y-axis. So the area of that strip would be a half y delta x. The area of the strip would be y delta x. The distance of that strip to the x-axis would be a half y. So the expression is a half y squared delta x. I take the sum of that. The sum of that then, of course, is where the integral comes in, half y squared dx. And on the left-hand side, that is going to be y bar multiplied by the complete area. I'm crashing a little bit, aren't I, with this previous line? So that would make y bar equal to a half the integral. Instead of y squared, let's write f of x all squared dx over the integral of f of x dx. So these two formulas here, do we like them? Do we not? They are just a little bit awkward, aren't they? So remember them or learn how to get to them. They're not given to you in the formula sheet. Okay, so let's start this question. So this first bit here, show that the coordinates of the centre of mass of the lamina are this. Whoa, look, 9 marks. Now, I have to admit, this isn't a proper OCR. That's not our exam board. It's the OCR MEI. So they're similar in style. But I think certainly the mark allocation is more. So we wouldn't get 9 marks for this kind of question. Shall I try and squeeze it in here? Don't know, it might take up a little bit more space. No, we should go underneath. So our function is 4 minus x squared. Right, to work out x bar. So it is, this one's the easier one to remember because it's very similar to the formula for working out a mean from a frequency table. So I'm quite happy with remembering that one. We want to work out, you can work it out inside that integral symbol, or you can, sorry, inside the fraction I'm meaning, or do it in 2 separate bits. I might just go for it. The function itself isn't that tricky, is it? I've got then 4x minus x cubed on the numerator dx. And I have got just 4 minus x squared dx on the denominator. Of course, I am dealing with my function between 0 and 2. So I'm going to have limits of 0 and 2 on these. I'm going to get 2x squared minus a quarter x to the power of 4 on the top. evaluating that between 2 and 0. And on the bottom, I've got 4x minus a third x cubed, evaluating that between 2 and 0. Okay, if I put that in there, 8 minus 4, of course, evaluated at 0 is 0. On the bottom, 8 minus 8 thirds minus 0. So that is 4 over 16 thirds, 3/4. Hopefully that tallies. Yeah, 0.75. Now the next one, the y one, I should probably go underneath. So to find a y bar, it's the same on the denominator, isn't it? So I've got the same, the integral of f of x dx happening down there. But what about the numerator? So the numerator is, well, I've got half of that distance and I need to multiply the y by the y. So that's going to mean half of f of x all squared. The integrals there, slightly more awkward, aren't they? So I've got 4 minus x squared all squared integrated between 0 and 2. The denominator is the same, isn't it? So that makes life slightly easier. So let's combine that half and that 16 thirds. So that's going to be 3 over 32. 16 minus 8x squared plus x to the power of 4. That is what I'm integrating with respect to x between 0 and 2. 3 over 32. 16x minus 8 thirds x cubed plus 1/5 x to the 5 between 2 and 0. 32 minus 8 64 thirds plus 32 over 5. Evaluating 0 is 0. 8 over 5. Yeah, so we get the correct answer there. So centre of mass is at, it was 3/4, 1.6, go on, I should be consistent. I'm doing mechanics, 0.75 and 1.6. Okay, so the effort there isn't the actual integration, is it? It's getting to the formula, it's remembering the formula or understanding how we get to the formula. Now, next part. So this lamina and another exactly like it. So what we've got here is the shape that we've just found the centre of mass of, and we've got 2 of them. And then there's also a rod here, PQ. So we've also got that. We've got to find the combined centre of mass of this shape. So it's told us that the y-axis is there. So I know what the individual centres of masses of each of these 3 shapes. Okay, so the length of that rod, I've done it far too long, haven't I? It just goes from there to there. So the centre of the mass of the rod, of course, is going to lie there. I know that the centre of mass of each of these is 0.75 and 1.6, so it'll be about there and about there. So of course I can define those in terms of the axes. So this is where we generally employed a little table. I think what I'm going to do is I'm going to represent those as just point masses. So that's my axis. I've got one there, one there, and one there. This has got a mass, so this is the centre of the rod. That's got a mass of 12g. This has got a mass of 6.5 g. Sorry, mass. I'm drawing them on as weights, aren't I? Because I'm adding the g there. And we know those coordinates are 0, 0. So that's the centre of the rod. I know that the centre of mass of the first lamina is 0.75, 1.6, but then the second one, it's starting 2 along, so it's going to be 2 plus the 0.75. So the second one will be at 2.75, but then it's going to be 1.6. And so we use these little tables, didn't we, to keep track of what's going on. So firstly, I've got the rod, and then I've got the first little sail, and then I've got the second little sail, and then we've got the total shape. So we could call this weight, but we tended to call it the mass ratio, didn't we? I don't care about those G's. I know that the masses of those would be just in the ratio 12 to 6.5 to 6.5 to 25. So I want the x distances. The x distances, well, the rod is situated at the origin. So both its x and y are going to be 0. I know that the first sail shape has got a centre of mass 0.75 and 1.6, and the second sail shape is 2.75 and 1.6. And of course, our total shape, that's what we refer to as x bar and y bar. And then it's just a matter of working them out. I know that the sum of all of those individual masses times by the distances is equal to the overall 6.5 multiplied by 2.75, and that is equal to the overall mass multiplied by the value of x bar. So that means that x bar will be equal to, if I work out all of that, 6.5, and type that in, 22.75 over 25. 0.91. 0.91, what we in centimetres, I don't know. Meters. And then if I do the same for y bar, 12, I mean, I needn't really have included that 12. 12 times 0 plus 6.5 multiplied by 0.75. No, it's 1.6, isn't it? I'm doing the y values. Plus 6.5 multiplied by another 1.6 is equal to 25 y bar. So y bar, 6.5, 13 times 1.6, 20.8 over 25, 0.38, sorry, 832 meters. Okay, find the coordinates of the centre of mass. So I would need to just express that as a point 0.91, 0.832. Okay, now I've got some ready prepared little shapes here because it was a little bit of a faff drawing them. Come down here though so I can talk about you. So very last part is to find the angle at which PQ makes with the horizontal. So I should say first that what is going on is that the rigid body is freely suspended from the point A, which is at 2, 4. So 2, 4, this point A up there. And then it is hanging in equilibrium, so it's not moving. So here is a representation of the shape that we've got. This is our centre of mass in green. and that is our point A there. Now, if you were to hang that so it was in equilibrium, what happens is that the forces going up, in other words, the tension has got to exactly balance the forces going down there, your mg. So the line through the center of mass and the point at which you're hanging is always going to be vertical. So the shape to be in equilibrium, this line through the point at which you're hanging and the center of mass will be vertical. Okay, otherwise it wouldn't be in equilibrium. You've got to have those forces balanced. This, of course, is my tension force up here. We're not asked for the tension force, but if we were, it would just be equal to mg. So what that means is we've transformed it into a very basic trigonometry problem. Don't waste your time drawing that. This is just for me explaining it to you. Please don't waste your time drawing it. It is far, far easier just to draw that line on there. Though that's a bit excessive, isn't it? Let's go with the blue line. To draw that line on there and then just refer to it. Okay, this is my vertical. The angle that PQ makes. So the angle that PQ was the rod here, wasn't it? So this is the triangle that we need to think about. So draw that triangle out again. There's my angle. Now I know that the center of mass, it's got a bit lost, isn't it? It's at 0.91 and 0.832. This is the 0.24. So I know that tan of my angle is the difference in y's over the difference in x's. 3.168 over 1.09. That makes theta equal to 71.0 degrees. Let's just go with 71. Okay, let's just check I've got the right angle. Oh, okay. It says the angle that PQ makes with the horizontal. Okay, I don't know, it seems a bit odd that it says horizontal, but easy enough. So what I found is I found the wrong angle. The horizontal would, of course, be this one here, but that just adds an additional line. I would obviously just now need to subtract that from 180. I think I'd always mark on my vertical. I think even if I knew, I'd still do the same as I've done here. Because that vertical line, this orange highlighted line, it's in equilibrium, isn't it? So just at the end. So angle with horizontal is 90 minus 71, so it's 19 degrees. Okay, I'll stop there and I'll do the remaining two in a separate video. It is, however, slightly shorter. I think it won't be quite this long. Okay, I'll see you in the next one.